In the first example problem for this chapter, we're told that there's an object moving around in a circular loop of radius 0.8 meters, and that object moves once around the loop every 2 seconds. For the first question of how fast is this object moving, we're told the object is moving at constant speed. So I'm going to choose to find the speed of the object by writing speed is distance traveled over the time of travel. Now, when I use this relationship, there's something I want to take a moment to be very explicit about. This relationship is only true if the speed is constant. If the speed is not constant, I am not allowed to use this relationship. You can see that very explicitly. If you think back to chapter 2 when we talked about 1D motion, we said final position is initial position plus v0 t plus 1/2 at squared. Now, if you are moving in a line and you are moving at constant speed, that implies your acceleration is 0. So I could, in that scenario, drop the acceleration term. And I'm allowed to choose my origin to be anywhere I want. Let's choose the initial location to be the origin. So that gets rid of x0. And what I'm left with is the final position, which will be the same as the distance traveled, is equal to the speed times the time. Because we were never speeding up or slowing down, the initial speed is also going to just be the final speed in this problem. So this relationship is true if you are not changing your speed. If you are speeding up or slowing down, you are not allowed to use this relationship. So with that having been said, we are told that the object is moving at a constant speed and it goes once around the loop every 2 seconds. So I could ask, how far does it travel every 2 seconds? So once around the loop, well, that's just going to be the circumference of a circle of radius 0.8 meters. So here I could say the distance is the circumference of a circle with radius 0.8 meter. And the time of travel once around the loop is 2 seconds. So I could say the speed is going to be 2 pi r over delta t. So I get 2 pi times 0.8 divided by 2 seconds. And when I put those numbers in a calculator, I get the speed as 2.5 meter per second. For part B of this problem, we are asked what is the centripetal acceleration of this mass that's moving around in the circle. To find the centripetal acceleration of this object moving in a circle at constant speed, we could use the equation A equals v squared over r. We found the speed of the object in part A of this problem, the 2.5 meters per second. We were given initially that the radius of the object's circular path that it takes is 0.8 meters. So I could write this as 2.5 squared divided by 0.8. And when I put this in a calculator, I find the magnitude of the centripetal acceleration to be 7.8 meters per second squared. Now, before I go on to talk about part C of this problem, I want to go on a bit of a side tangent. You might look at this equation we used for the centripetal acceleration and say, that looks very similar to the radial component of the acceleration vector that we talked about at the end of the previous video. Are these two ideas related, and if so, how? They have a very similar equation between them. So, to go off on this side tangent, we are not going to talk about this problem specifically. Let's talk about the general case of an object that's moving in a circle, and let's allow that object the possibility that it might be speeding up or slowing down. So we will not require constant speed. Now, previously, when we talked about acceleration, we said acceleration is a vector quantity. That means this quantity has both a magnitude and a direction. We very often would break up these vectors into their components and call it ax and ay. But when I talk about circular motion specifically, sometimes it is more convenient to talk about the component of acceleration that is in the same direction as velocity or parallel to velocity. And sometimes it's good to talk about the component of an object's acceleration that is perpendicular to the object's velocity. If I want to fully know the object's acceleration, I need to know both components of the acceleration. It's not enough just to tell you one component of the acceleration. So when we are talking about an object that is moving in a circular path, we could talk about the component of that object's acceleration that is parallel to the direction of motion or parallel to the velocity. So A tangential is the component of the acceleration that is parallel with the velocity, and that is written as delta V over delta T. A radial is the component of the object's acceleration that is perpendicular to the direction of motion, perpendicular to the velocity vector, and that is written as V squared over R. Now, if you think about how we defined acceleration when we first learned about it, we said that acceleration is a change in velocity. We could think about velocity and remember that velocity itself is a vector quantity. So velocity has both a magnitude and a direction associated with it. You could change velocity either by changing the magnitude of your velocity, that would be like saying you're speeding up or slowing down, or you could change the velocity vector by changing the direction that it points. In other words, change the direction of travel. A tan is the component of the acceleration that will cause you to speed up or slow down. And A tan will always be either parallel or opposite, anti-parallel to the direction of the velocity vector. A radial is the component of the acceleration that causes you to change your direction of travel. And A radial will always be perpendicular to the direction of the velocity. Now, to connect these ideas with what we're doing here, we said at the beginning of this problem, we are assuming the object is moving at a constant speed. So for this particular problem, A tangential will just be equal to 0. So I can write this is equal to 0 for this problem. And when I think about how is the magnitude of a vector related to its components, the magnitude of a vector could always be related to its components by the Pythagorean theorem. Now, for this specific example, one of the components of the acceleration vector is 0. So the entire acceleration vector for this problem will have its entire magnitude just be equal to the radial component of the acceleration vector, because for this specific example, A tangential is 0. Now, the rule, as I said, the direction of the tangential component of acceleration is always in the same direction or opposite velocity, depending whether you're speeding up or slowing down. The rule for the direction of the radial component of the velocity is the radial component of the velocity always points inward towards the center of the circle. So for this specific example, the direction of the centripetal acceleration is going to be inward towards the center of the circle. Now, what direction is towards the center of the circle? Well, that depends where the object is in its circular path. If the object is right here in its circular path, then towards the center of the circle points to the right. If the object is over here in its path, the direction that is inward points to the left. However, this specific problem asks what is the direction of the acceleration when the object is at the top of its loop. When you're at the top of the loop, the direction that points towards the center of the circle is going to be straight down. So I would say the direction of the centripetal acceleration when you're at the top of the loop is straight downward. Next example problem, we are told that there is a fan spinning at a constant rate, And we are asked first to find the distance that the tip of the fan blade moves when it goes once around the center of the fan, and then we're asked to find the speed of the tip of that fan blade. So if I draw a picture of this, here's the tip of the fan blade. At this instant in time, the fan I drew is spinning in a clockwise direction, so that tip of the fan blade will have a velocity at this instant that looks something like this. And the tip of the fan blade is 0.15 meters away from the center of the fan. So I could look at this picture and notice that once around the fan, the tip of the fan blade will trace out a circular path. So we're basically asking, what is the distance in total of that circular path? Well, that will just be the circumference of a circle. So I could look up the circumference of a circle is given as 2 pi r. I could write that as 2 pi times 0.15. And when I put this number into a calculator, I get the distance traveled when the tip of the fan blade goes once around the fan is 0.94 meters. For part B of this problem, we are asked to find the speed of the tip of the fan blade. Now, because this fan is not changing its rate of rotation, I can write speed as being equal to distance traveled over time of travel. In general, you are not allowed to always write this. You are only allowed to use this equation when your speed is constant. If your speed is changing, you cannot use this equation. I went on a whole tangent about that earlier. So in this particular problem, though, the speed does happen to be constant, so that makes our life a little bit nicer for solving this. If I know the distance that the tip of the fan blade travels when it goes once around the center of the fan, I have a distance. If I could find the amount of time it takes, then I would have enough information to find the speed of the fan. Or there might be other ways we could solve this. So we are given that the fan undergoes 1,200 revolutions per minute. Okay, well, one revolution is once around the fan. That is something that does not have units. That's basically counting the number of times around. And minutes is not usually the unit of time we want to work with. We would rather work in seconds. So first, let's convert this number into revolutions per second. So if I convert 1,200 revolutions per minute times 1 minute over 60 seconds, then I would find that the fan is spinning at a rate of 20 revolutions per second. So the fan is going boom, 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 very fast, 20 times each second. Okay, at this point, let's determine the speed. So if once around the fan the tip of the fan blade travels this distance, 20 times around the fan, the tip of the fan blade will travel 20 times this distance. So I could write the speed at which the fan blade is traveling would be 20 times 0.94 for a distance divided by 1 second. The fan blade will travel this distance once around the fan, and it will travel 20 times this distance around the fan every second. So I could put this number into a calculator and find the speed of the fan is going to be 18.8 meters per second. In part C of this problem, we are asked to find the acceleration of the tip of the fan blade. Now again, the fan is spinning at a constant rate, so we could just use v squared over r. That will be our rate of acceleration. So I could do that by writing a equals v squared over r. Now we found the speed at which the tip of the fan blade is moving. That is 18.8 meters per second. And the radius of the fan blade from the tip of the fan blade to the center of the fan is 0.15 meter. So I find the acceleration of a point on the tip of the fan blade is going to be 2,356 meters per second squared. Finally, for part D of this motion problem, we are asked to find the period of motion. So period is the amount of time it takes to go around once, the amount of time it takes to complete one cycle. We previously found that the fan is spinning at a rate of 20 revolutions per second. So we are asking if the fan goes around 20 times in 1 second, how much time does it take the fan to go around once? So I expect it will be less than 1 second because it does more than 1 revolution every second. So this number of 20 revolutions per second is basically the frequency of the rate of rotation of the fan blade. So I could write this 20 as being my frequency. And then if I remember that period is 1 over the frequency, I could write that as 1 over 20. And I get the period of the fan blade is going to be therefore 0.05 seconds.